All right. So good morning. Definition of the spectral radius. We usually write the spectral radius. The spectral radius matrix. So the spectral radius of the matrix, which we usually write it as this, of a matrix A is defined with the maximum lambda, where lambda of A. So an important theorem of this is that if you have a matrix A, which is, let me say, trying to the Euclidean norm of that matrix is nothing but a spectral radius. Two, spectral radius of the matrix is less than the norm of the matrix, right, for any natural norm. Three, okay, so of course, I'll write here so this theorem just connects the matrix, the norm of the matrix, to the spectral radius. The spectral radius, we have said, is the maximum eigenvalue. So, example is that example for you to understand. Oh. Example, if you take a matrix A, it's 1, 1, 0, 1, 2, minus 1. We say that A times will give us 3, 2 minus 1, 2, 6, 4, minus 1, 4. The spectral radius of A transpose, to compute it, right? We know we need to do the eigenvalues. So the determinant of A transpose A minus lambda I. If you do that, then you get cube plus 14 lambda squared minus 42 lambda. And this is that lambda is equal to 7 plus or minus 12. So the Euclidean norm is the spectral radius we spoke about, and this is nothing else, maximum of eigenvalue. 7 plus 7 minus square root of 7. And definitely this is the square root of 7. And this is 3 points, approximately, right? 3.1. So this is how we do the law of the matrix computation.
Look.
Hello.
So where is the I?
Where's the what?
The I.
What I?
What was this? Oh, I thought this was a complex number, sorry.
There's no complex number so far.
Okay. But what if you have one of the engineering values as a complex number? What do you do?
If you have what?
One of the engineering value as a complex. For example, maybe you have one is 0 and then the other is 7 plus I. What would be now the
So it means
percentage
if you have, let's take example something like this, where you have, if you have maximum, let me write it well.
Yeah. Of 2.
No, don't worry. All right. So if you have this one where you have the maximum of maybe 1, then you take the modulus, right? If it's a complex number.
Yeah.
And then 1 minus square root of 3i.
Yes.
Right?
Yeah.
So you try to take the modulus, right?
Okay.
So this one you get the maximum of 1, 2, 2. And such an example, you know that the maximum is 2.
Okay.
So the definition that I want to give is what do we mean by something we call convergent matrices, right? Let me write it here. So we call an n by n matrix A convergent if the limits of that matrix Ij as k goes to infinity goes to 0 for each I 1 to n, and for each j also 1 to n. So example of convergence, if we say matrix is convergent, right? If we take an example A, such that this is half, 0, 1/4 half, a matrix like this, we can compute the powers. So this is what we mean. Compute the limits of the powers of the matrix will go to 0. So we can compute the powers. It means, let me say, we can compute the powers of A. That means you compute A squared. If you do that, you have 1/4, 0, 1/4, 1/4. You can do the same for A3 up to AK, and you see that as you go on, your AK will be half to the power k, 0, Is there?
In this sense, powering A is just powering each element in A, because I thought now when we power A, we multiply A times A.
Yeah, I mean, you can.
It
Let
won't be the
me.
same.
Yeah, we can check.
Do we multiply now the row by column?
So A squared means
A times A.
A times A.
Yeah.
A cubed means A squared times A.
Yes.
So all right. So I wanted to run just for you to see. There's nothing really strange with this. So if you run this one, then you have 2 to the power k plus 1. And then you have half to the power k as well. So the limit of these, you can see that the limit of these, the limit, if you take the limits of half of k as k goes to infinity, you get to 0. And the limit of this guy as well, as k goes to infinity, also goes to 0. So if we have such a k, right, so the power k is 0 as k goes to infinity. The limit as k goes to infinity of k over 3, k plus 1 is also 0. It's also 0. Then we say A is a convergent matrix. But you see, if we take note, the spectrum radius of the matrix that we have, of this convergent matrix, is half. If we take the determinant and find the ideal values, it's half. So you will see that there is a connection between spectral radius of a matrix and the convergence of the matrix as well. Right? Because we said that if the matrix is convergent, then the limit of its higher order terms, the limits of the matrix, right? The limit, this one, the limit as k goes to infinity of ak is 0 for each I and for each j as well. So because of this idea of the connection between the spectral radius and the convergence of the matrix, we are able to write a theorem because of this, right? That gives us the equivalent. We say that the following statements are equivalent. One, A is a convergent matrix. Two, the limits as n goes to infinity of a to the power n is 0 for some natural norm. 3, the limit as n goes to infinity of a to the power n is equal to 0 for all norms. 4, the spectral radius of the matrix is less than 1. And then 5, the limit as n goes of a to the power n of x is 0 for every x.
How were you able to develop that, Doc?
What?
This one I've circled there, limit. From a quarter, how you came up with k over something?
Yeah, I said, no, you are writing, you have a matrix A, you find a matrix A squared, A cubed, and so on. So this is a sequence. You should be able to derive such sequence, right?
I didn't have idea about that.
If you have half, and then you go to 1/4, and then you go to 1/8, you should be able to generalize this. And this we generalize as half to the power k for the first part. For the second part, you see that if you keep doing your multiplication, for instance, if you take A3, here, A3 will give you 1/8, 3/16, 1/8. Do you understand?
Yeah.
Yeah, so it's not the same. You need to then find the how to generalize this, the sequence being generated.
Okay, I've understood.
You get it?
Yeah.
So I think you get something like you should get. We started with 4. It will move to something like 3/16. Then it will move to 1/8. Then and so on and so forth. So you can generalize to k over 2k plus 1. Two k plus 1. So that's how can we come by such a formulation. Okay. So the proof, I think so far I've not really done any proof with you guys. The proof is in one of the popular books. The proof is in The proof is in Isaacson, but I'll give you a better reference. I'll give you the reference for that. Isaacson and Keller. This is on page 14. But I'll give you a better reference in the main lecture that I'm still finishing on. Okay. So that's really something I wanted you to know about eigenvalue, spectral radius. This is particularly, the spectral radius is particularly important because we use it a lot. If you have
Excuse me.
an iterative, yeah, I'm listening.
Excuse?
Yeah, I'm listening.
Okay, sir. Please, I want to understand what is the application of this convergent matrix to this what we are doing. You know, like I want to understand what we are going to use this convergent matrix to do.
Yeah, I mean, because you need the idea is that you need if you are developing an iterative scheme, or if you are developing an iterative scheme, you need the idea of the spectral radius, right? The spectral radius gives you an idea of the convergence of your system. So if you have an iterative scheme, usually once you have this iterative scheme, you have, right? You can write it as x k is equal to txk minus 1 plus c, where we have k to go, and we have x of 0 given arbitrarily. It's given arbitrarily. Sorry. But what happens is that arbitrarily. Okay, but what happens is that if you know the spectral radius of this guy here, right, then you're able to tell about the convergence of your iterative scheme. I don't know if you understand what I'm saying. So the idea of the convergence of the matrix, as we stated here, is that if you have a convergent matrix, then you know that you can connect it to the spectral radius of the matrix. And that's the most important thing about it. Is the powers, because the idea of this convergence matrix is just the powers of the matrix, right? Powers of the matrix. And it tells us that the powers of the matrix, as the matrix grows, right? As the matrix grows, all its entries become small and small, and they approach 0. All the entries become small and small and approach 0. This is very important because today I'll give you some exercises to implement, like the gradient descent method. When you implement them, you see that you are getting powers of matrices. You need this idea of the convergent matrix because they are connected to the spectral radius of your matrices as well. So you can easily say that if you have a matrix and then you have a span of some vector space where the vector space is based on the powers of this matrix, you can easily write, or you can easily know when what are the main vector space, what encompasses this vector space, the span. You can know it. This is the idea that we need this convergence of the matrices. It's just to tell us that when we know the powers of the powers of the matrix will become small, right? And that is almost all the entries are going to go to 0. All entries approach 0. And you'll see it very soon. These are definitions, so we'll call them very soon for you to understand why we need this idea. Okay. So, as I said, if you have an iterative method, and so let me come down. So let's convergence of iteration, right, method. Can we say something about the convergence of the iterative methods? Lemma 1. If the spectral radius, that's why I went back. If the spectral radius satisfies this condition is less than 1, then I minus t to the power minus 1 exists. And we can write I minus t to the power minus 1 as I t plus t plus t squared and is equal to, you can write it as t to the power j. Simply because maybe for the first time I should write 2 so that we can enjoy proofs. You can find the tx corresponding eigenvalues, right, of the matrix T when I minus t of x is equal to 1 minus lambda of x. We have an eigenvalue of t when 1 minus lambda is an eigenvalue of I minus t. However, we know that the spectral radius is bounded below by the maximum eigenvalues, and bounded above by 1. So that if the eigenvalue is 1, we know that it cannot be true. Hence, I minus t inverse of 1. If you take Sm, so that this is equal to 1 plus t squared plus t to the power m, then I minus t times an Sm will be plus t to the power n minus t squared, sorry, plus all the way to t m plus 1. And this will be nothing but I plus t m, sorry, I minus t m plus 1. So you can see that we have convergent matrix T, right? T is a convergent matrix. So it doesn't matter how much power we try to write it, we can easily tell that because it's a convergent matrix, the limit of its power goes to 0, approach 0, right? So since T is convergent, we know that the limits of I minus t Sm, because I minus Tsm is what we have, right? If m is going to infinity, is the same as the limit m goes to infinity of I minus t to the power m plus 1. And this will be I, because t is convergent. And thus, we can say that I minus t of minus 1 will give us the limit m going to infinity of Sm which will be the same as I plus t squared to infinity. And this will be infinity 0 t of j. All right. Another important thing is that for any arbitrary initial condition given in Rn, the sequence from our iterative scheme, right, which is defined by xk to the power s to the power k t xk minus 1 plus t for k greater or equal to 1, it converges to the unique solution of x is equal to tx plus c. If and only if the spectral radius of t is less than 1. Again, you can write a proof. Assume that the spectral radius of t is 10. X to the power k is tx to the power k minus 1 plus c. And we can write the next iterate as T of T x minus k minus 2 plus C plus C, right? So basically, iteration means you have x, k, c, x, k minus 1 plus c. You solve for this k here. And then your next one, so if you want to go to maybe kx, k plus 1, then you do tk, txk plus c. But xk we know, so it's t, right? txk minus 1 plus c plus c. So that's what we are trying to write here. K minus 2. And then this will become, if you just expand, is t squared k minus 2 plus c plus I of c. So if you continue in that format, you have tk x0 plus bracket c k minus 1 plus c plus I of c. Since the spectral radius the matrix T is convergent, and the limits as k goes to infinity of t to the power k x0 is 0. And then from the lemma above, right, from this lemma that we wrote here, I call it lemma 1, let me call this theorem 2. From lemma 1, we know that the limits as k goes to infinity of x of k is the same as the limit as k goes to infinity t to the power k x0 plus this whole term here, which we know as sum j in 0 to infinity t to the power j and c. And this whole term, we know what it means. It means we can write it as 0 because this is convergent matrix plus this term here, we know what it means. It means I minus t inverse of c. And so finally, you have I minus t inverse of c. So hence, the sequence f to the power k, k from 0 to infinity, converges to the vector x, which is equal to I minus t to the power minus 1 of c, and x is equal to t of x plus c. So we have proved that if you take any arbitrary initial start for your iteration, you create a sequence which converges to a unique solution of your iterative scheme. If and only if the spectral radius is less than 1. In this particular proof, we assumed that first the spectral radius is less than 1, and then we showed that truly, if the spectral radius is less than 1, any initial starts for your iterative scheme will converge to a unique solution. Of course, the converse, if and only if, converse, right? Converse, we need to show for the converse, we show that for any z in Rn, we have the limits k goes to infinity, ck of z to be 0. And minutes. Okay. So then let me go back and then make a reference. So let me call this okay, maybe I try to number 1, theorem 2, lemma 3. We use lemma 3, theorem 4. Okay, so we have this case that if we take z in Rn, then the limit of tk of z goes to 0. And by theorem, the convergent theorem 2, by theorem 2, we know that this is an equivalent form of the spectral radius being less than 1 from theorem 2. If you take z to be an arbitrary vector, and you take x to be unique solution to x equal to tx. If you define x to the power 0 to be x minus z, and for k greater or equal to 1, so xk to be txk minus 1 plus c, then x to the power k, k from 0 to infinity converges to x. Also, it means that if you take x and subtract the convergence, you can write tx plus c and subtract txk plus minus 1 plus c, and this will give us tx minus xk minus 1, so that x minus x to the power k is equal to tx minus sk minus 1. And if we proceed in a similar manner as we did now, then we have x sk minus 2, and so on. So we have tk x minus 2, which will be the same as tk offset. Hence, the limit of tk offset k going to infinity is equal to the limit k going to infinity tk, which is equal to the limit k x minus xk equal to 0. So z is in Rn was arbitrary. This implies that T is a convergent and the spectral radius is less than 1. So, and this ends the proof. Let me also go here. This also ends the proof here. Okay, so we know about the convergent matrix, and then we know about the spectral radius. We know we can connect them, that the powers of matrices approach 0. And so we can use that idea and then connect it to that the spectral radius of our matrix is less than 1. And then in that case, we can connect the two, that if we take any arbitrary starting point for our iterative method, for any iterative method you really want to define or design in the future, you must test this, that any starting point, any starting vector that you take, if you define your iterative scheme in such a format as sk is equal to tsk minus 1 plus c, then we know that it converges to a unique solution, right? It converges to a unique solution if and only if the spectral radius of that matrix C, right, of this matrix C here, if a spectral radius is less than 1. That's really, really a very powerful information, or a very powerful idea. Of course, as a follow-up to that, we can say that if, let me call this corollary 5, right? As a follow-up, if the norm of the matrix is less than 1, right? And C is a given vector, then the sequence xk, k from 0 to infinity, defined by x to the power k to be tx k minus 1 plus c, converges for any x0 in Rn. to a vector X in Rn, and the following error bound also holds. So the error bound holds. What does it mean? It means one, the norm of X and Xk is bounded by the norm of your matrix T to the power K, X to the power 0 minus X. And then 2, you can have X minus Xk again, is bounded now by T to the power K over 1 minus T to the power, not to the power of X1 minus X. Okay. So the quick question you can ask yourself is, for instance, the quick question you can ask yourself is, how can we use this in terms of what we know, maybe Jacobi and Gauss-Seidel, right? So example, let's take, in the case of Jacobi, we have Sk to the T of J, Sk minus 1 plus C. In the case where our Tj was T inverse L plus U. In the case of the Gauss-Seidel, we have Tg x a minus 1 plus C, where our Tg was T minus L inverse times U. Okay, so if we go back to these theorems that we have stated here, right? What does it mean? For instance, if we take these two, let me write this as Cj and Cj, right? We say that if the spectral radius of the Jacobi or the spectral radius of the Gauss-Seidel is less than 1, then the sequence x to the power k, here from 0 to infinity, will converge. Point to the solution of our matrix, of our system, of Ax is equal to B. This is exactly what this means, right? So you can write your Jacobi in this sense, and then also, so again, of course, you can check again for the relaxation method, where now Xk is equal to T of R, A minus 1 plus C of R. So you can check what is the spectral radius of this T of R. You can check. If it is less than 1, then you are also sure that you have a convergence of your iteration or iterative scheme to your system of equation that is given. Okay. Okay. So I'll use that to bring an end to this particular point, because I want to now talk about some of the modern iterative schemes. At least I want to talk about one of them. Because in your assignment, I hope to give some of these schemes to you as assignments for you to implement them and test them on your own, and then submit them for scoring. So it's important that we try to test. I try to explain some of these modern schemes to you, and we call them gradient schemes, right? We call them the gradient schemes. But maybe before I go to the gradient schemes, I mentioned somewhere here about error bounds, right? I mentioned here about error bounds. So maybe I can spend some few more minutes to talk about error bounds. Okay, so usually if you have your system AX is equal to B, all that you are trying to do with these iterative schemes is trying to approximate or derive an answer that is very close to the solution of your system. So if you have AX is equal to B, all you are trying to do with this X, CX plus C is trying to create a sequence XK, which is really close to X. So in that sense, what we do is that we can create a residual. So let's say if X bar is an approximation to X of AX is equal to B, then we can write a residual, right? We can write a residual vector R, which is B minus AX of R, AX bar. Which has a property that the norm of R is equal to the norm of B A X bar. Is small. Then X minus X bar would also be small. Example, if you have AX, example, if you have AX is equal to B, where your A is 1.001, 22, hello. So we can write, if example, if you have such a system, right, where we have 1.001 and 2230.1, we know that our X if we solve it, so this x1, x2 will be 1, 1 transpose has solution. However, so let me just do A 1, 2, 1.0001, 2, B 3, 3.0001 transpose, then X is equal to A. So if you solve such a system, you will get X to be 1, 1. So, however, if you have a poor approximation of this X, a poor approximation X tilde or X hat, sorry, which is 3, 0, come. Has a residual R minus R is equal to B minus AX bar, which is 3.0001, which is B minus A 1.0001, and then if we take the X bar, which is 3, 0, then we'll have 0 and minus 0.0002. So that the infinite norm of R is 0.0002. So that's although the norm of the residual vector is small, the approximation X bar, which is 3, 0 transpose, is 4. So from this example, we can go another theorem that if you suppose that an approximation x hat to the solution of A equal to B, where A is a non-singular matrix and R is the residual vector for x bar, then for any natural number x minus equal to R, A inverse, and if x is not zero and B is not zero, then x minus x bar over x, the norm, can be bounded by A times A inverse of R over B, or the norms. The proof for this is usually basically very straightforward. If you take the residual of R to be B minus A star, and we know A to be AX, and A is non-singular. A is non-singular. Then x minus x hat x bar would be nothing but A inverse of the residual and this implies that, of course, I'm calling one of the theorems that we use. Now we talk about the error value. So x hat x bar is equal to A inverse, which is less than or equal to A inverse of moreover B is equal to A. We have B is less than or equal to A times x. So 1 over x is less than A over B. And x minus x bar x will be A inverse over B times R. This will end proof. So this theorem actually gives us, okay, so this implies that the norm inverse Okay, this is norm, the inverse matrix, the norm of the inverse of the matrix, and the product provides an indication, gives us an indication of the connection between the residual vector and the accuracy of the approximation. And the norm that we are talking of, right, is not it's any natural norm, any convenient norm that you want to take will always be fine. Now, I want to talk about the condition number. The condition number of the non-singular matrix A. Relative to the norm is sometimes people write it as kappa A, but in some groups they use A as well. This is the condition number. So if you use this idea that A is the condition number, then if you go back to this theorem again, we can substitute the condition number, right, into this equation, right? So with this notation, we can rewrite x minus x bar, which we said was this guy, right? A inverse R over B as x minus x bar Ka R over B.
In the left-hand side, this over norms of x is there.
You saying?
Yes, x, the norms of x minus x bar over the norms of x.
I mean, there's a relative one. So if you do like that,
Yeah.
So this is for the relative. So this is for the relative norm. So from the idea of the condition now, we can write matrix well conditioned if the condition number is close to 1 and it's a still condition. If the condition is significantly larger than 1, greater than. So in that sense, condition, right, means that more residual vector, a small residual vector implies accurate, approximate, What does it mean? You take the matrix A, it's the same matrix that we took. Then the infinite norm, for instance, 3.001. The inverse is 10,000, 10,000, 5,000.5, 5,000. And the norm of that is 20,000. That's condition number in terms of the infinity norm, in this case, where we say it's equal to the norm of A, the norm inverse will be 3.0001 times 20,000, and this will be 60,000. So you see that the condition number here is very big, right? It's very big. So definitely an ill-conditioned matrix.
So does it mean that now this matrix is ill-conditioned?
Yes.
Okay.
So if you connect your ill-conditioned matrix to the error bound, and you can connect it to your iterative convergence as well, then you know that if it is ill-conditioned, right, if you go here to this case that we have, if it is ill-conditioned, it is a very big number. The error is bounded by a very big number. And then that you can bring it back again to the solution of your iterative scheme, that you probably will not get a unique solution. So this is a bit about the kind of things that we usually deal with. We deal with condition number, spectral radius, and then the convergence matrices. where A is an n by n matrix. And this gives us an idea of a convergence of an iterative scheme. Combine all these, if you link all of them well, it will always give you an idea of a convergence of an iterative scheme.
So
Sorry.
this is so much helpful to someone who is planning to develop a convergence scheme of.
Yes. So if you so I'm going to now talk about gradient methods, and then if I talk about the gradient methods, then we'll discuss some of these things about them. But then, as I said, in this for me, for your assignment, I'll give you some problem to solve. And then this problem, if you solve it, you probably an iterative scheme or something you implement, then you have to check, is it convergent? Is it convergent scheme? What does it mean that it is convergent? What are the things that are necessary to check that this scheme really will converge? For me, this is the main idea that I need you to understand.
All right.
So because I'm going to talk about conjugate gradients, and then when I talk about conjugate gradients, I'll then talk about the convergence of conjugate gradients. So you need to understand what the residual vector is, and then you'll be able to then use it to kind of understand what we mean by conjugate gradient and then its convergence as well. Is it okay?
Yeah, it's fine. It's fine.
Okay, good. So next is that I'll start talking about conjugate gradients. So conjugate gradients are very powerful. They are part of the gradient methods, and also one of what we call the Krylov subspaces. They form, they are a subset of these methods we call the Krylov subspaces. Okay? And they are really powerful. It's so powerful that is why it is one of the methods, the earlier methods that people started when they started doing artificial intelligence development. But for conjugate gradients, you need a symmetric positive definite matrix. So of course, we'll then, so some of the questions you have to ask yourself is, okay, so if your matrix is not a symmetric positive definite, what will you do? Does it mean you cannot do conjugate gradient, or there's a variant conjugate gradient that you can use when you have such a problem? And then the answer is yes, there are variants that you can use when you have problems in that direction as well. So let me okay. All right, so that I say we start with let us consider matrix A to be SPD. By SPD, I mean symmetric, positive, definite. Symmetric, positive. So if we have a vector x, let's say x, which is a solution to the positive definite system, AX is equal to B, if and only if X minimizes the inner product minus 2 where by definition, I mean X, Y, the inner product just means X transpose Y. Proof is that if you take X, B, which is not 0, with fixed vectors, and T is a real number, then Jx dv x plus dv ax plus dav minus 2x plus dv of b, which is equal to x ax plus t v ax plus t x av plus t squared v av minus 2 xb minus 2t vb. Let's expand. Which is the same as x ax minus 2x b plus 2tv ax minus 2t vb plus t squared v av. So that's x plus v division x plus 2t ax minus v plus t squared v AV. Since X and V are fixed, we can write an HT function to represent X plus T of V. Then H assumes the minimal value when HT when the derivative is zero. So that means that when you have H prime of T, then V of X of TV, find the derivative 2 of V X minus V plus 2T of V of AV. The minimum occurs when T high is minus V X minus V over V of AV, which is V minus AV V of AV. And that's H, if we put TV, T hat in terms of H, then we will get X minus 2 VB minus 2 over V AV times V minus AV plus V minus A over V of AV squared V of AV. Which is equal to G of S minus which is equal to G of X minus V B minus AV squared over V AV. For any vector, we will not we have Gx plus G hat of V to be less than Gx. Unless B minus AB is 0, in which case G of X is equal to X plus G hat of V. So suppose that X dagger, okay, satisfies an AX dagger is equal to B. Then VB minus AX dagger is equal to 0 for any vector V and G of X cannot be made smaller, right? Any smaller than G of X dagger. So thus S dagger is really a minimizer of G. On the other hand, if S dagger is a vector that minimizes G, then for any vector V, we have G, X dagger, T hat is greater than G of X dagger. Thus, VB minus AX dagger is 0. And this implies that B minus AX dagger is 0. And consequently, maybe I should write it here. And consequently, AX dagger is equal to B. So to begin the conjugate gradients, some things that we need, or some of the terminologies usually is a search direction. You need a search direction. You need a search direction. And then once you compute the search direction, so the search direction is basically this T that we are trying to do, right? It gives you a search direction. So we compute the search direction. And then after we try to compare these residual vectors, which gives us also an idea of which the next steps to take. So that's basically some of the main ideas that's around conjugate gradient. Okay, so it's not a lot, but I want to really try to explain for you to understand the whole concept of conjugate gradient. So we need a search direction. So that is, we choose X as an approximate solution to AX dagger is equal to B and V not equal to 0. Which is actually the search direction in which to move. Away from X to improve the approximation. So if you take R to B minus AX, then T okay. So if we take R, which is the residual, if we take R as the residual, be the residual vector associated to X and the set direction T, which we saw V minus AX of V of AV will be nothing else but V of R of V of AV if R is not 0 and if V and R are not orthogonal, talk about it, then X plus TV gives a smaller value of G than G of X. And is presumably closer to X dagger than X. This suggests the following. Pick X naught to be an initial approximation of X dagger and let V1, direction V1 not equal to 0, be an initial fetch direction. For K1, 2, 3. So this is really what the conjugate gradient is. Now, compute TK. Compute TK, which is VK, V minus AX, K minus 1, all over VK, AVK. And then compute your next K, SK, as SK minus 1 plus CK to VK. Then choose a new direction, VK plus 1. The aim is to make this selection so that the sequence of approximations xk, k from 0 to infinity, converges rapidly to x data. To make such a choice, to choose this search direction, we consider G as a function of the components of x, where x is a vector in Rn. Thus, G of x1, x2, xn, xax minus 2x of b, which is equal to n, I1, j1 to n, aij, xixj minus 2 I1 xivi. If we take partial derivatives with respect to xk, then we have dg of dxk of x, and this will give us aki xi minus 2b. Therefore, the gradient of g is gx dg dx1 x dg dx2 of x dg dxn of x transpose is 2ax minus b, which is nothing else but 2 minus 2r, where r is the residual vector for x. Of course, I've written this in the term, so of course, we also know that if you write this here, the gradient of gx, then we know something about this from calculus, right? So let me say that from calculus, we know that the direction of greatest descent, greatest decrease, okay, in the value of g of x is the direction given by minus g of, that is in the direction of the residual. The method chooses VK plus 1. You carry K to VA x to the power K. And this is called the method of steepest descent. The advantage, one of the weak points for linear systems this method has a slow convergence. However, an alternative is to consider a set of non-zero direction vectors v1 up to vn that satisfies vi, av, avj, v0 if I is not equal to j. This is called orthogonality. Condition. A matrix orthogonality condition means and the vectors that you are using, the vectors v1 up to vn are said to be orthogonal or orthogonal. So in that sense, you will just have to go back to this method and then now try to modify it in such a way that we are getting some new search directions. Okay. So let me save this. Okay. Okay. So we have an A orthogonal orthogonality condition that is vi avj is 0 if I is not equal to J. And A orthogonal, that is the vectors 1 up to n are said to be A orthogonal. We know that if we have A orthogonality, okay, we can show that let me say 4. For A orthogonal vectors, associated to a positive definite matrix. So A orthogonal vectors associated to a positive definite matrix. A are linearly independent. This yields the search direction VK, VK, V minus A, SK minus 1, VK, A, VK. VK, A, VK. And SK, if you go to X, K minus 1 plus GK of B. Okay. This choice of the search direction gives convergence in at most n steps. And this, we can write in a theorem that if you have some A orthogonal vectors of non-zero vectors associated with a positive definite matrix, A, and you choose an arbitrary initial value, then you can define the search direction B minus AX, B minus 1, VK, AVK, and x of k, x k minus 1 plus g of k for k1, 2, then assuming exact arithmetic, we have ax of n is equal to b. Yeah, so the proof will be an assignment. So how do you go about all this? I mean, that should be the most critical point. How do you go about all this? So this is what you do. Just a few more things, then we are done. Example, if you have a matrix 4, 3, 0, 3, 4 minus 1, 0 minus 1, 4. If you take V1, if you take V1 to be 1, 0, 0, and V2 to be minus 3 over 4, 1, 0, V3 minus 3 over 7, 4 over 7, and 1. Then, if we take V1, AV2, we need to check orthogonality. We mean nothing else but V1 transpose of AV2. 1, 0, 0 times A 4, 3, 0, 3, 4 minus 1, 0, 3, sorry, 0 minus 1, 4, and then V2 minus 3 over 4, 1, 0 is equal to 0. Then you have V1, AV2. You put V1 there, you put your A, 4, 4, 4 minus 1, 0, 0, 3, 3, minus 3 over 7, 4 over 7, 1. You also get 0. And then if you take V2, AV3, you also got 0. Just to show that V1, V2, V3 are A orthogonal sets. So let's just say if we were given 4, 3, 3, 0, 4 minus 1, 0 minus 1, 4, x1, x2, x3, and you're given 24, 30 minus 24, with exact solution S dagger 3, 4 minus 5 transpose. If we start with an arbitrary initial value 0, 0, 0 transpose. Since B is 24, 30 minus 24 transpose. We have that the residual B AX of 0 is B minus equal to B is 24, 30 minus 24. If we assume that X0 is 0, is a 0 vector, then the next step is now take the first vector in the orthogonal set, multiply it by residual. This is V1 transpose of R0. And this will be 24. Again, take your first vector A of V1. This will be V1 transpose AV1 to be 4. And then you compute your direction T0, which is nothing but V1 of R0 over V1 of AV1. This is 24 over 4, which is 6. Then now you can compute your X, right? X1, which is going to be X0 plus T0 of V1, so 0, 0, 0 transpose, plus 6 of 1, 0, 0 transpose, which is 6 of 0, 0 transpose. So this is your X1. And now you want to go for X2. So for X2, you have to start with R1. And then R1 is B minus A X1. We know B, we know XY, we know A. So we can just compute 0, 12 minus 24. Then now we can compute our set direction 1, which is V2 of R1 over V2 AV2. And this will be 12 over 7 over 4. This will be 48 over 7. Then next we do X2. X2 is X1 plus T1 of B of 2. And this will now be your 6, 0, 0 of transpose plus 48 over 7 . And this will be 6 over 7, 48 over 7, and 0 transpose. This will now be your X2. So you see now the steps are compute your R1, compute your T1, then compute your X2. Compute your R2, compute your T2, then compute your X3. So that's the steps. That is now if you follow, you see that you will need. So first, x1 is this. Now we compute x2 is this. Now we can continue to do x3 because we know from the theorem that we know from here that the set direction will converge in n steps if you have a matrix of size n. You know that you only need to do n computations. So here we need 3 computations to get our x, the final value. We have done first one, x1, x2, and now to do x3, the same steps I have highlighted that now you need R2, right? So R2, you need R2. You need your R2, which is b minus ax2. Because we have x2 already, it's easy to compute. 0 minus 120 over 7. Then we need C2, which is B3 R2 over B3 AB3. And this will be nothing but minus 5. And you need your x3, which is your x2 plus C2 of B3. And if you compute this, you have 3, 4, minus 5 transpose. And this is exactly what we meant by exact solution. That when we said that with exact solution, this, right? And now truly with 3 iterations of our technique, we are able to derive finally so the solution converges after n is equal to 3. Of course, the question is, how do we define, or how do we determine, or how do we find, how do we determine these A orthogonal vectors, right? And the examples were given. That's the main question. How do we determine these, the A orthogonal sets? Theorem. This theorem gives us an idea of how to determine these A orthogonal sets. So maybe as you write it a bit here, that the following theorem shows the orthogonality of the residual vector. Vectors R of K and the direction vectors V of J. Theorem. The residual vector Rk, where K is equal to 1, 2, and so on to n, for a conjugate gradient or a conjugate direction method satisfies R of K, V of J is 0 for J 1 to K. Here, we choose the search direction. VK during the iterative process so that the residual vector RK are mutually orthogonal. We construct the direction vectors V1, V2, and so on. And the approximations X1, X2, and so on by starting with an initial approximation X of 0. And then we use the steepest descent direction R naught is equal to B AX naught as the first search direction. V1. If we assume that the conjugate direction V1 up to Vk minus 1 and the approximation x1 up to sk minus 1 have been computed with sk minus 1 to be sk minus 2 plus tk minus 1 and vk minus 1. Where V AVJ equal to 0.
Excuse me, doctor.
Yeah, and RRJ is equal to 0. Or I not equal to 0. Yes, I'm listening.
I hope we are summarizing. The next lecture is in 30 minutes. The prof is already here at the building. He told me.
The next lecture is in 30 minutes.
In the next 30 minutes, yeah, he's going to be here because he's already at campus here. In fact, he wanted to come at 1:30, and I told him we are still in some class. Give us more 30 minutes.
Okay.
Pardon?
So I'll come around.
Okay.
I'm summarizing. Then, because I'll give you exercises. So you see, in this idea of the conjugate gradient, what we spoke about was that you need a matrix. The matrix you are dealing with is a positive definite, symmetric positive definite. So your assignment that I'll give to you will be very similar in the same side, but now you have to try to find some convergence estimate as well if it is non-symmetric. How will you derive the same ideas? How will you derive the same thing? So let me try to summarize exactly how to choose this search direction or this search vectors, okay, direction vectors. And I said if you do that for that, you have this case and okay. So what I'll do next is that I write for you the algorithm for the conjugate gradient. That if you take k from 0, 1, you compute some alpha wait. So let me see. Okay. So not alpha, so it is C, CK. Where your TK to N, where your TK is RK minus 1 of RK minus 1 over VK AVK. Then you compute your XK is SK minus 1 plus your TK of VK. Then you compute your residual RK minus 1, which is minus TK of AVK. Then you compute an SK, right? Which is now RK of RK over RK minus 1, RK minus 1. And then now you compute your VK plus 1, where it is now RK plus SK of VK. Okay, so this then becomes your algorithm exactly the same. So, but in the example that we created here, you see that when I started, I gave you here this orthogonality vectors, right? Orthogonal orthogonal vectors. I gave them to you. The question is, how do we create them? So in the conjugate gradient algorithm here, we give you a way to create these vectors here using the search direction, your residual that you compute as well. So those are the main steps that distinguishes the descent method from the conjugate gradient method, right? The other side is that then is we can then talk about the error bound, which is what I want to do to complete this session. The parameter sk guarantees that x guarantees that the error bound is minimized. Along the descent direction. VK. File. If you go back, so this one here. This one here. File SK is choosing to ensure that the new direction VK plus 1 is A orthogonal. With VK. That is A of VK transpose VK plus 1 should give us 0. We have a proposition that says that if A is symmetric positive definite, then the conjugate gradient CG method converges after at most n steps. And moreover, the error E of K so this E of K is nothing but X minus X of K. At the kth iteration with K less than N is orthogonal to P of J. Let me say to to the Z direction for J01 up to K minus 1 and the arrow X minus SK is bounded by 2 CK 1 plus C2K of X minus X0 to C given by the condition number of A minus 1 over and C is given by the square root of the condition number of A minus 1 over the square root of the condition number of A plus 1. Okay, so this is really one of the critical things that I wanted to address. But this is now like state of the art, really in terms of how we address more recent times problems of this nature, big problems. Of course, some questions we have not answered, right? Questions we have not answered. What if A is non-symmetric, but positive definite? And then 2, can we combine both direct and iterative methods? Three. Three. The conjugate gradient method is a class. Okay, maybe this is not 3. It's just some notes, right? Notes. The class of iterative solution techniques, right? Which is called Krylov subspace. Okay. So the conjugate gradient forms part of solutions. We have a whole class of solutions that follows this technique of trying to find orthogonalities and search vectors, and trying to find this type of using this type of ideas. And we call all these kind of techniques in general a Krylov subspace technique, right? So usually what happens is that once you have found your residuals, once you have found your residuals, once you found your residuals, so you have a span, and then you have, let me write it well. So you see why we also spoke about A, R of 0, have your A2, R of 0, and so on, up to AN minus 1, R of 0. And this, we call them pile AN, A of R. And this space is called pile of subspace. So you see that in general, this pile of subspace is trying to talk about the convergence of matrices, right? And then the residuals. And then it uses it to create a certain vector space where we are guaranteed that we are going to find our solution, the solution to the problem, let's say. Okay, so apart from that, there are methods, some methods that we call the preconditioned methods as well. So we have preconditioned conjugate gradient methods. So now I'll just mention some of these names. We have the general minimal residual method. We have the biconjugate stabilization methods, and so on. And all of these fall into this class of solutions called Krylov subspace methods. Of course, there are other very, very increasingly very important methods. The multi-grade methods. We have the algebraic, and we have not. So the multi-grade, we have many of them. So the multi-grade, we have the algebraic multi-grade, I'll call it NG. We have the geometric multi-grade. We have some iterative methods called the multi-level methods. Okay, and these ones now people try to combine direct methods with iterative methods. So here, right, try to address here this kind of problem where they combine both direct and iterative methods. And then they fall into these methods. Then we also have domain decomposition methods also come into this as well. So basically, all in the sense of AS is equal to B, you can do direct, 1, 2, you can do some iterative, 3, you can combine them, combine direct and iterative. Okay. So maybe I'll just stop here. I'll stop here so that you can prepare for your next lecture. Hopefully we can have another lecture before July begins. I think that we have a lecture next week, 29th, but I will need another some 2 hours to complete the topic, the course, the part that I'm teaching. Apart from that, next week Thursday is 3 hours. So next week Thursday, it means we'll do a longer hour. We'll do 3 in the morning. We'll take a break, and then we'll do 2. Is it okay? John?
Yeah. It is fine. So we'll need that one meeting, then we'll also need another 2 hours.
Yeah, so well, what I'm saying is